Do not use the space. Sorry, thanks for reminding me.
So let me see the live stream.
Do not use the space. Sorry, thanks.
Okay, everything's good. Hey, Jinping. See Bob.
All right.
You okay?
Yeah. A little late, but I look forward to this.
Yeah, I see Courtney here. So the good thing is after the March 14, Jinping will, because the summertime will be 9 p.m. Beijing time.
Oh yeah, that's gonna be a little better.
Yeah, but still we appreciate many Chinese colleagues still, coming up here, even from 10 p.m. to 11 p.m. Sometimes we see Yoshi Saito, 11 p.m. They still attend most of the talks.
Worth the waiting.
So John and David, are you ready?
Sure are.
Okay, so turn on your camera. Let's get started. And let's see here. Okay, cool. Okay, good morning to American colleagues, and good afternoon to the European colleagues, and also again good evening to our Asia colleagues. Welcome again to this World River and Delta Source to Sink webinar series. Today is our this year 2021 the number 14 webinars. So we invite Dr. John Swartz and Professor David Mohrig, and they used to be John, I believe, is a student of David, but John now in the Water Institute of Gulf, and Dave, of course, in the University of Texas at Austin. So before I introduce them, and I want to also say, and so far we have almost 50 Source to Sink webinar talks already archived on the YouTube channel. And I want to say we have been tried from beginning, try to be more inclusive. And so we open our invitation to everybody in this communication if you feel your research also this river delta source sink related, you want to give a talk, I will be very happy to schedule your talk here. Particularly, we hope we can get more talks for those rivers we haven't talked about. For example, those Russia river system, or those high latitude river, or small river system. Particularly for our colleagues, like our women colleagues, people of color, or underrepresented group, and we welcome them. Even your language is not English. As soon as you can speak with accent, it doesn't matter. Like my kids always make fun of my pronunciation, my accent, but we are just want to be more inclusive and have more in this river and delta related study. So if you have somebody you can recommend it to me, please go ahead and recommend it to them. As I said, doesn't matter the gender, race, or culture, or background. So we are living together on the same planet. Okay, so also this coming Friday, Christoph, he will talk about the organic carbon from a Congo River to the deep sea fan. I think that's a fantastic source to sink study, but also involve the carbon issues. And please mark your calendar and this Friday at the same time. And so John is a research scientist at the Water Institute of the Gulf, and he graduated from UT Austin, I believe, working with David. And so his interest is climate change, coastal fluvial morphodynamic, flood plan for geomorphology. And so I think his research work on that Rio Grande River system. And David is Associate Dean of the Research and of Professor Jackson School of Geoscience and University of Texas, Austin. This is a great school for the geoscience education and research. And so there's David used to be a postdoc at University of Minnesota and also a senior research geologist at ExxonMobil, and since 2021, 20 years as assistant professor all the way to full professor and the associate dean. And his research is sedimentary geology, coastal fluvial river system, sediment gravity flow, and a couple of things I want to point out. David become an AGU fellow 2016, and also is become the award of the Pete John Medalist receiver. So congratulations, Dave, and this is great. So I think now I will give the floor to John and David. So John, now you can begin to share your screen.
Sure, thank you, Paul. Let's see here. All right, that looks good.
Great.
Looks great.
So thank you, everyone. Thanks for joining us today. As Paul mentioned, we're going to be talking today, David and I together, on a few different aspects of the larger integrated Rio Grande system, which is a huge continental scale drainage basin in Western North America that both David and I feel has been relatively underappreciated and underrepresented in a lot of studies of depositional systems and source to sink systems. And it's a system that both of us, and as well as our larger research groups, have been trying to kind of pick away at and really try to understand better for well over a decade now, both in the terrestrial realm, like the delta that you see here to the left, as well as the marine realm, like the submarine fan you see here to the right. And we're going to show components of both of those today, all to try to understand what the dynamics of the source are and how they manifest in the depositional processes of these sinks. So the integrated Rio Grande system is a really impressive and complicated drainage basin, delta, and submarine sedimentary system that could span a whole year of these sorts of talks talking about different aspects of it. But for today, what we're going to try to do is really start in the sink and try to work our way back up to the source. We're going to go from deep time to the modern. So little bit of the structure of the talk today is we're going to start with just a brief introduction to the Rio Grande for those who aren't familiar with the drainage basin, why it's as important as it is, and why it has some features that make it a little bit different from other studies that or systems that you may be more familiar with. And we're going to start with the Rio Grande submarine fan system to look at the terminal sink for what has been draining out of the larger Rio Grande basin. And then we're going to look at the evolution of the lower Rio Grande River and associated delta. And I just wanted to kind of frame everyone, get everyone framed for the context of the system with this really impressive shot of the river on the delta at Mission, Texas from a helicopter, just showing some of the beautiful meanders and sedimentary features that exist as part of this river. So if you like rivers, if you like meandering, if you like sedimentary products, this is the system for you. And it's, again, one that has received relatively little attention by the broader community. I also want to emphasize that this is a broader effort beyond what myself and David are going to show today. We have a lot of co-authors and colleagues involved with this work, particularly our co-authors Tim Gouge, Sean Gulick, and Daniel Stockley, and a huge other team of associated folks that we just work with informally and bounce ideas off of as we've been working on this system for the last decade. What we can learn a ton of different things from this really critical watershed, and I hope to emphasize throughout the course of this talk that there's really interesting and surprising sedimentary dynamics within each of these depositional components that we're going to study in detail today that have a lot of broader implications for geomorphology, sedimentology, stratigraphy, and land use practices. So a lot of the things that we've discovered in the Rio Grande are a little counterintuitive or don't quite fit into the broader framework that we've been developing as a community based on our studies of other river systems. But I think David and I will both propose that what we're learning in the Rio Grande has much broader implications outside of this system alone. So to just orient everyone to what the Rio Grande, or the Rio Bravo del Noche if you're in Mexico, is, it's a massive watershed that drains the entire western North America from southern Colorado all the way down to northern Mexico, and then empties into the western Gulf of Mexico. And the lower Rio Grande, as defined in the portion of Texas and Mexico, has been kind of long understudied, underappreciated, and poorly understood, particularly from a sedimentary geology or geomorphology standpoint. We have several really important opportunities, though, through studying the system to really try to better our understanding of as a community of what the sedimentary dynamics and stratigraphic products of a semi-arid continental drainage basin are, as well as really concretely link terrestrial and marine sedimentary processes through an almost unprecedented data compilation that we've put together over the last decade. This system is impressive in many ways, but we're also going to really kind of dial in and show in detail the evolution of the submarine fan and the terrestrial delta over the late Pleistocene to Holocene. But there's a lot more that we could go into on a deeper time or even a more modern aspect, but we're going to focus on that time period today. So some key characteristics of the system. The overall drainage basin is roughly 500,000 square kilometers. As I mentioned, quite a large size. I think the fourth largest in North America. Has a significant endorheic component that I'm not counting in that drainage area, as you can see here. It captures the southern Rockies and northern Mexico, and so transverses some really interesting tectonic regions, as well as some really rugged and steep terrain that laid to a pretty high sediment supply. And the depositional area, even just the terrestrial delta associated with this system, is over 13,000 square kilometers. And it's the second largest epicenter in the Gulf of Mexico after the Mississippi. But the modern river is extremely heavily modified and has very low stream flow. So when you look at larger compilations of delta size, river size, and so forth, it often appears a lot smaller and a lot less impressive than the actual size and extent of its epicenter actually is. So the basin itself is commonly subdivided into several regions for management and study purposes. And so when we talk about the Rio Grande, there's been a ton of work done on regions that are more commonly referred to as the upper and middle Rio Grande, which are the regions of Colorado and New Mexico, going back to the 1800s. So when I say the Rio Grande's relatively understudied, I'm really referring to the downstream depositional portion. There's been a ton of work by many great people in very many different communities on the upper section of the river. Then as we transverse down the river through the middle Rio Grande, we reach the Rio Conchos, which is the main Mexican tributary, as well as the main source to the lower Rio Grande River. And then finally, we reach the lower Rio Grande, which forms the border between Mexico and Texas. And then finally, the terminal downstream end of the terrestrial system, which is called the Rio Grande Valley colloquially, but is actually a delta for the majority of it. The basin has an extremely long history of anthropogenic modification going back to the 1600s. And those modifications continue today, and the overall kind of framing of the Rio Grande in a modern context is one of challenge. Challenges in terms of water scarcity, challenges in terms of flooding, as well as management of agricultural versus population versus ecosystem interests. The basin itself is a really interesting one in the sense that in terms of the stream flow and climate, you can almost divide it into two separate rivers. So the upper Rio Grande in Colorado and New Mexico is almost entirely governed by snowmelt from the Southern Rockies. But however, by the time you reach Fort Quitman, the river is often completely dry with a just completely dry bed. It's not until the Rio Conchos joins the river at Ojinaga that the lower Rio Grande is rejuvenated by those flows. But the way that that precipitation occurs and the style that it takes is very different from the upper river. So whereas the upper river has that snowmelt in the spring, the lower river is really governed by the North American monsoon. So it has a very seasonal intermittent climate that leads to a very flashy stream flow. So when we look at the Rio Conchos stream flow coming out into the lower river, you can see what I mean here. This is a great study by Ingel Blanco back in 2013 that looked at Rio Conchos stream flow. And you can see that the kind of average daily stream flow for these different months is really low for most of the year, and then really shoots up into the late summer, early fall, and then decays back down into the winter. So these flashy flows under both natural and anthropogenic conditions are going to lead to some really interesting sedimentary dynamics, as we're going to see in the lower river. Just in terms of what that difference means for comparison of like an arid versus a humid system in terms of stream flow, the arid climate punctuated by seasonal, highly variable discharge within the lower river. So the discharge of the Rio Grande at Brownsville on the delta can vary between 2 to 3 orders of magnitude intra-annually and has associated punctuated sediment transport. If we compare that to a perennial system, which is the kind of system that's more commonly studied globally, they have a much more consistent stream flow. So here I've just pulled the basin of the Trinity River in East Texas, which is a very humid region, and plotted a representative water year for both systems. So in blue, we have the Trinity at Liberty. In black, we have the Rio Grande at Brownsville. Both of these are in cubic meters per second on a log scale. And what you can see is that even though the Trinity, of course, has base flow and flood periods, it's always relatively consistent, and the base flow is always relatively high, whereas the Rio Grande base flow can decay to almost nothing. And then when you go into the flood stage, it can go up by about 3,000 to 5,000 cubic meters per second from zero. So this punctuated discharge leads to really different dynamics from these perennial systems. In terms of the tectonics and basin setting, again, it's a really interesting system. It's incredibly complicated, and I'm by no means an expert in all of this. But I just want to point out a few kind of key elements or key things to think about. So the Rio Grande itself originates, as I mentioned, in the Southern Rockies. So if we look at this long profile put together by Marissa Rapash as part of her Earth Science Reviews article in 2017, you can see that we start up in the extremely high relief, high elevation San Juan Mountains, and then we transverse a number of provinces. We go through the Southern Rocky Mountains, through the Rio Grande Rift, through the Eastern Basin and Range province, and then finally reach the Gulf of Mexico. There's a lot going on this figure here, but I just wanted to emphasize that there's a lot of really interesting dynamics in terms of the integration of this system. You can see on this profile several nick points, especially up in the upper section of it. And there's some evidence from different studies that show that the final basin integration in terms of this system existing as a kind of cohesive over 3,000 kilometer long river system may have happened relatively recently, as young as maybe 600 to 800,000 years. So the size of this integrated continental basin may have been a relatively recent phenomenon, and we might see expressions of that within the Western Gulf of Mexico when we go looking in the marine realm. So what are the sedimentary processes and depositional record of this continental system? That's the kind of overarching set of questions that we're really trying to get at in this talk today. So we have our source here. We have the the Rio Grande Basin in Western North America, and then we're going to look at two different sinks. We're going to look at the Pleistocene to Holocene submarine fan, so in the offshore from the shelf edge down into the deep basin, and then we're going to look at the Holocene to modern river and delta. These two sinks together comprise the majority of the material sourced from this large basin over the last 20,000 years. In the marine realm, we're going to be able to look at the linked shelf edge delta and fan systems and how continental margins grow. We're going to see some really interesting interactions between sedimentation and salt tectonics. And we're also just going to see an incredibly impressive sequestration of sediment volume, so over 12,000 cubic kilometers. Within the Holocene to modern river and delta, we're going to see the formation of an enormous and broad terrestrial delta through backstepping and river avulsion. And we're also going to have an opportunity to look at how fluvial morphodynamics vary within an arid climate setting. So I think with that, I'll stop sharing and let David take it away for the marine section.
Great. Good morning, everyone. Oops. Let me get this up. Okay, everyone can see my screen?
Yes.
Great, thank you. So I'm going to spend the next few minutes talking about the deep marine component of this source to sink system. And I want to also make the point that what John and I are showing you today is actually only half of the system, in the sense that we're really focusing on the information that we've been able to collect on the US side of the border. This is an international system, and the work on the Mexico side is not nearly as advanced. So we're really just looking at half of this system. I want to begin by looking at the system and making sure that everyone realizes how interestingly different this set of distributed channels that you see on the ramp-like system of the Rio Grande differs from a classic Mississippi submarine canyon and Mississippi fan-like system, which is often a better known system when we think about the deep marine environment, where we have a feeder channel that actually bypasses a lot of sediment into a submarine fan at significantly greater depth. We're actually looking at a system in the Rio Grande where we have highest sedimentation rates that end up being associated with our highest slopes, and we're actually producing a sedimentation pattern that's associated with progradation of a very, very large cliniform. And we will hypothesize that this style of deep marine sedimentation is very much affected by the style of avulsions and the number of avulsions actually happening on the shelf edge delta. Working on this system, we have the advantage of a lot of seismic data. We've interpreted, this is the royal we, because actually John has done most of the interpretation, over 25,000 kilometers of 2D seismic data. You can see the grid here that's very nicely laid out. There's also some academic seismic data that you can see this pattern that is a little less organized, which is of course what we actually collected. And there's also core and biostratigraphic information. So we can use this to understand how this evolved and what sort of sediment volumes are associated with the system. And one of the things that we were very much initially interested in is, why is this big fan-like ramp situated in this province that otherwise is really dominated by salt tectonics? You can see both to the north and to the south a series of diapirs and mini basins evolving, but something that looks very much like a constructional fan in between. So I want to take you through some of the seismic data that we have available from that grid. And I want to begin by just making sure that everyone realizes what they're looking at here. This is going from toward the coast off. So this is at right angles to the shelf slope break. And we're looking at a panel where the thickness of the deposit is about 1 kilometer and the extent of the line is 35 kilometers. So, and there's a 15 times vertical exaggeration. And you'll see this exaggeration in this same exaggeration in all of the seismic lines. So one of the first things we learned was that this is a very, very structurally complicated system that we don't actually see when we look at the surface. We're actually seeing a lot of structure, but a case where sedimentation and remobilization of that sedimentation seems to be winning. And so even though there's a whole series of shelf edge deltas here associated with the prograding of this margin, the older ones are very, very significantly partitioned by the normal faulting that we see in this system. But we can use this grid of seismic data to map around regional horizons to start to get a sense of depositional patterns connected to the seafloor topography. We have some age control that comes both from up in the shelf edge delta systems. This regional mapping has allowed us to define 3 sort of shelf edge delta complexes, the youngest labeled A, and then a B, and then the oldest labeled C here. Core and that we collected from the A complex gives us ages of about 11,000 years, and core that was collected from toward the distal end of the submarine system can just be constrained to the Wisconsin, so to the last glacial period. So we're really we're going to be focusing on the system that's associated with the last roughly 100,000 years or less. So I showed you those 3 delta complexes, and so you can see the youngest one here that is defined by a basal horizon that has been interpreted through the area that we're going to be discussing, and then the green, and then finally the older yellow complex. You can see right away that while on the seafloor, the structure of the shelf edge system is dominant, the depositional topography, when you go into the subsurface, there's a tremendous amount of structural deformation associated with salt tectonics. But this structural deformation has actually been overwhelmed by sedimentation in this particular area. And for orientation, you can actually see the line from which this particular section was drawn. So what we're going to do in the next couple of slides is look at what the character of the deposit is using the seismic data, and we're going to follow around this basal surface of the youngest delta and ramp complex. And again, remember 15 times vertical exaggeration and really great thicknesses, 2 kilometers and an extent of about 60 kilometers in the horizontal. So that was up here in a shelf edge setting. If we look at a profile going down the system, we can see a couple obvious things happening. First, the degree of structural deformation with depth associated with mobile salt is really spectacular and not at all represented on the seafloor, the modern seafloor, where it is really limited in its extent because sedimentation seems to be overwhelming the salt tectonics. We can also see by looking at the thickness between that basal surface and the seafloor that we have a very consistent sedimentation pattern that one would expect with the progradation and growing of a clinoformal system. Whoops, too far. If we go now down and we look again at a strike line, moving from that dip line to a strike line toward the distal end of the area we've been studying, here again is that basal surface that has been mapped around, and you can see the salt tectonics with depth, but a minimal expression of that in the area of highest sedimentation rates, and also a significant thinning as we move down the system as well. So this sedimentation pattern is very much connected to the channelized system that is focusing and delivering the sediment to the deep ocean. So we want to look at what those channels look like and how they in fact are connected to the transference of sediment from the shelf edge delta system into the deep marine setting. I should also point out that we really go from a set of parallel channels here into an area where we start to see a tributary-like or collection of the channelization as we move downward in the system, and that there seems to be enough sedimentation that we don't see any sort of channel or indentation associated with a canyon. And this map of the thickness of the sediment accumulation between that basal blue horizon and the seafloor gives you a good sense of why that is. You can see the really hot colors here. If we take sort of a reasonable seismic velocity here, these reds are associated with almost a kilometer of sedimentation, and then you go down into the greens and into the blues, and you can also see very much that the thicks are associated with the clustering of these channels. And all in all, this sediment package here represents, as John has already said, over 12,000 cubic kilometers of of sediment that was deposited in the late Pleistocene to early Holocene. Now let's look at what these channels, how they're working and how they're changing in their style as we move from the shelf edge system down the slope. So we move a distance from the shelf edge. There's a very remarkable change that is connected to sedimentation. If we look at transect 1, which is up here closest to the shelf edge break, there's really very little expression. Just this high reflectivity package here ends up becoming the channel in this area. I should also point out before we look at the other 3 transects here that this green line separates what we're interpreting as a Holocene mud from the very late Pleistocene, early Holocene channelized deposits. As we move to transect 2 here, we can see that we're starting to develop some relief associated with this channel. Most of this is negative relief associated with this channel. As we move then down to transect 3 and transect 4, we actually start to see levees developing. So we're now having not only a bypassing basal surface as this channel developed, but we're also aggrading the margins of the channel and developing what end up being very impressively levied submarine channel system as we move down to 4. And so we're getting deeper and deeper channels through these 2 processes of creating channel relief, and the sedimentation rates are decreasing as we move down the system, with the hypothesis being that we're having a greater transport efficiency and then a lower sedimentation rate associated with these systems. I should also point out one other characteristic about this ramp system. While the channels are doing a lot of the moving, we cannot also mention the mass transport complexes. You can see where, hopefully you can see where my mouse is. This reflectivity is all associated, and some of this reflectivity down here, with remobilized slope. This slope is in a constant state of failure. You can actually see some of the tongues associated with those failures even expressed on the seafloor. So if we now put some of this together and we look at A through, this is A, B, C, D, and E, and we look at these channels and the slopes associated with these channels as we move down these 5 systems and the deposit thicknesses that are found underneath these channels, we see a remarkable correlation between channel gradient or slope, which starts out high at between 2 and 3 degrees, and then all converges to a value of about half a degree, and between that correlation and high sedimentation rates. High slopes, high sedimentation rates, and as both decrease with distance from the shelf edge, we see a pattern of significantly lower deposition and lower gradients associated with this. This sort of ramp-like system is not as well studied and is not as thoroughly published on in the geological literature, but there are some very nice studies from like the Magdalena Deep Marine System, the Champion Deep Marine System, and the Fuji Einstein Deep Marine System, and we will soon be adding this one to this. And the final thing I want to point out here is that when we think about the source to the sink, we were able to look at this shelf edge delta to slope system and put together the volumetrics, and you can see we have a large, over 300 cubic kilometers of sediment tied up in the shelf edge deltas here for this late Pleistocene, early Holocene system, but we have almost 3 times that in the slope deep marine system as well. So the real repository is this deep marine ramp system, and that's where the records we need to go to look at for the long-term history of these systems. So this slide simply summarizes the points that I've already made. One is that there's a tremendous amount of sediment caught up in the deep marine system. We have this very systematic change in the form of the channels as we move down the system and in the pattern of sedimentation, and that we have a system with many channels that are probably associated with a very highly evulsive shelf edge delta system here, not unlike the modern system that John is going to take over the driving again and tell us about starting now.
Cool, thank you, David. So, as David just pointed out, there's a lot of really interesting features and things we can learn from the deep marine system. But one of the commonalities, one of the things I think we both really want everyone to take home is that the style of construction of the continental margin that we're looking at here is likely in some way related to the evulsive nature of the delta itself. And so we're going to look at that in broader detail. But I first want to make the point that the shelf edge delta systems that were feeding the submarine slope system persisted into the early Holocene as evinced by our radiocarbon dating. But if we zoom out and we look at how the system got from where it was at the shelf edge to where it is in the modern terrestrial realm, you can actually still see evidence for potential intermediate delta systems on the mid-shelf. So we plot up a set of 2-meter contour lines, as I'm showing here in black. You can see actual still preserved lobes and top sets of these intermediate deltas as the system is backstepping its way across the shelf before it reaches the modern position. What data we have from the modern delta indicates that it reached this position in about 5,000 to 7,000 years. And so we have this pattern of Holocene backstepping and aggradation. So the system was actively aggrading at the shelf edge until roughly around 11,000 years ago. And then it backstepped towards its modern position, occupying several mid-shelf positions along the way. But importantly, we don't see any evidence either in the offshore or within the terrestrial for significant flooding followed by progradation back over a flooding surface. Instead, what we see is evidence for backstepping and continuous aggradation, but just kept moving its way back up towards its modern system. And then it reached its current position in roughly 7,000 years ago, if we believe the oldest dates, and it's been stable and aggrading in that position since then. So let's look at what that system actually looks like. So let's look at the modern Rio Grande River and Delta. So here I'm showing just a LiDAR image. If you want to read more about the river itself, you can look at our 2020 paper in JGR. But we're looking at a compilation of LiDAR data from the US and Mexico, because as I mentioned, in this portion of Texas, the Rio Grande defines the border between our two countries. And what we can see, though, is that the delta itself, both on the US and the Mexico side, is comprised of tens of sinuous alluvial channel belts formed by river avulsion. So you can see all the sinuous alluvial ridges crisscrossing their way around the delta surface. And we can also see that within the modern channel, or the active channel as shown in black here, it maintains a sinuous alluvial character across the entirety of the delta. So this modern river has super elevated levees above the delta floodplain for almost 450 kilometers. It's not a system that's kind of heavily incising into the delta surface itself. If we look at some panels in close in, you can see the incredibly sinuous character of the river system, as well as the enormous number of cutoffs associated with it. We have dates for many of these cutoffs that we can see along the modern river, and a lot of these are actually historic in age. They occurred even into the early 20th century. So if we look at the broader Holocene evolution of the delta, again, as I mentioned, the surface of the delta is covered with these abandoned channels, which are locally called resakas. These resakas, which are shown here in the kind of thin dashed black lines, are continuous channel forms that can be as short as 10 kilometers or as long as 100 kilometers in length. And you can see if I wasn't telling you that they weren't a portion of the active river, they look indistinguishable from the modern Rio Grande river channel, which is shown in the kind of thicker dashed black line here. And the reason why that is that these resakas actually maintain their channel form even though they've been abandoned by avulsion, as well as acting as the local topographic highs. Additionally, these resakas form really crucial wetland habitat for the overall delta, because at least historically, they would be flooded with annual floodwaters from the modern river and actually acted as basically the only freshwater sources across the surface of the otherwise arid delta system. In yellow here, I've just plotted some of the avulsion nodes just so you can get a sense for how highly avulsive this system was. Again, there's dozens of avulsions across the US and the Mexico surface at the actual modern topographic surface of the delta, and then many more contained within the delta stratigraphy itself. If we actually went down to one of those resakas and stood on it, you'd see what I mean about its super elevation. So you can see here, I'm standing on the edge of one of the levees of the resaka. So this was one that was probably abandoned a few hundred years ago. And you can see the sweeping sinuous curve of this resaka relative to the floodplain and the estuary of the broader delta. Many of these resakas, as I mentioned, are still watercourses. So if I look at Google Earth here, just from this little bridge section north of Brownsville, again, you would be, if you didn't know, you would think that this is just what the actual river looks like, and it's almost indistinguishable from what the modern Rio Grande looks like. However, this is a system that's been abandoned for probably about 1,000 years, but they still act as watercourses in many cases, whereas others have been infilled for agricultural purposes. If we want to understand the early to mid-Holocene Rio Grande a little bit better and really understand what that transition looks like from when we went from the shelf edge to its current position, we're actually incredibly fortunate to have some interesting core data sets that were collected by Kenneth Fulton and ExxonMobil back in the 70s. So we go to the northern section of the system to look at these northernmost Rasakas here. Again, just notice the incredibly interesting sinuous channel forms of these channel belts that are still preserved on the delta surface, still have the channel geometries preserved remarkably well. But we actually have some deep cores that gave us basal sands that have ages associated with about 5,000 years ago or 7,000 years ago. And that lets us get a time scale on how much deposition has occurred since then. So in both these cases, we know that the delta appears to have started grading in this location about 5,000 to 7,000 years ago. And since then, we've had about 10 to 20 meters of deposition in this region. If we look at the cross sections that were associated with that, we can see a similar story. So we see that the delta has been grading in this current position by, in some cases, up to 40 meters since 7,000 years ago. But more importantly, we see that the entirety of the delta stratigraphy is comprised of these numerous generations of fluvial avulsion, incision, and aggradation to create the amalgamated delta surface. So within these cross sections, you can see the incredibly complex subsurface stratigraphy associated with the creation of a channel body by avulsion, its continued lateral migration forming these larger sand lenses, followed by avulsion away somewhere else in the delta, leading to the deposition of the overbank sediments. And this story plays out over and over again across the delta. But again, we've just created an enormous package of fluvial deltaic sediments within a relatively short period of time. So we can also, though, actually go and look at the stratigraphy for ourselves and not just look at the paper records from the 70s, because this delta is being really actively mined for sand, both for construction as well as coastal nourishment projects along the Gulf Coast. And so these sand pits provide some really interesting stratigraphic context. And so here I've just zoomed in on a LiDAR panel on one section of this Rasaka, and you can see in here the blue colors indicate deeper depths. This particular sand pit has been mined out almost entirely across the old point bar of this Rasaka, and we can go actually and take samples and do stratigraphic sections and really see what this delta looks like in the subsurface. So if you go down to some of these sand pits, they're pretty impressive in their scale as well as how much material is just being removed. But we can see that we have, at least in this case, exposed 4 to 6 meters of that fine-grained, fine to medium-grained fluvial sands, mostly dunes, topped with about 2 to 4 meters of draping silts and an overall surface elevation above sea level of about 3 meters. So they can't dig deeper than this because this is where it just starts filling up with water too quickly. So some key observations that we can observe within these stratigraphic pits is that these old channels post-abandonment by avulsion are still mantled with silts and muds that even though we're tens of kilometers away from the active channel. So this surface here, you might be able to point to, based on some of the evidence that we saw in the field, as being where this channel was abandoned by the river avulsing to some other location. And yet we still have pretty significant deposition across the entirety of the Rasaka, but it's mantling it and draping it and just propagating that channel relief upwards. So these abandoned channels still route floodwaters and sediment and still continue to aggrade the delta, even though we're now many tens of kilometers away from the active channel. So this leads to some interesting implications in terms of how delta systems and coastal plains can aggrade and build in locations that aren't actively being visited by avulsion or by proximity to an active channel. If we look at another pit here, we can see a similar story. So it's about 6 to 10 meters of fluvial sands, a 2-meter Danny Stockley for scale, and then again, a mantling of about 2 to 4 meters of draping silts and muds. This panel is particularly nice because you can actually see really, really well expressed in the surface the dune cross strata that are making up the majority of these deposits on the delta, and is also why they're such high value quarry targets for sand. So we get a really interesting sense of how the Rio Grande Delta grows and maintains itself, or at least used to. So the delta surface builds through the avulsions of the main channel at all these avulsion locations that are still preserved. And then the abandoned channels that are left behind by that avulsion still act to route fluids and sediments and solutes through those abandoned channels during flooding. So those former channels, in a sense, act as intermittent distributaries to build the delta across the entire area and not just proximal to what the active channel is. These channels also form the topographic highs on the delta, which is otherwise a really low relief, relatively flat plain, and so are really important for the routing of stormwaters during flooding. However, as I mentioned, a lot of these have been really significantly modified by human activity, and as a result, the ecosystem and hydrology of the delta in its modern state is incredibly challenged. So what about the modern river? I've shown a little bit about the kind of evolution of the Holocene delta, as well as some interesting characteristics of the resakas and how it avulses across the surface to build this feature. But there's a lot that we can learn about studying the active river channel itself. So as we've seen in our geomorph community over the last few years, and even within this Source to Sink seminar, there's been a lot of interest in trying to understand how alluvial rivers adjust towards the coast, in particular in response to the association of transition to the backwater zone. So there's significant changes in channel morphology and sediment transport associated with alluvial rivers as they transition to the backwater. And there's been a lot of work done by many different authors trying to understand the linkages between that transition and what it means for lateral migration rates, changes in channel geometry, avulsions, and so on. But we have an interesting opportunity within the Rio Grande to understand what the link is between the discharge variability of an arid system like we're studying and the resulting fluvial morphodynamics. So if we look at like a plot from Mike Lamb in 2012, a kind of common plot of what the difference is in the backwater zone between low flow and high flow and the associated changes in deposition or erosion, most of these studies have been done on systems that are perennial, like the Trinity, so systems that have a relatively low base flow to flood variability. But what about systems like the Rio Grande, where I showed that flood variability can be 3 to 4 orders of magnitude? So to do this, we're going to look again at the modern channel here. So we can still see all the resakas, but we're going to focus just in on this 300-kilometer reach of the lowermost Rio Grande, shown in black here. And we're going to look at a few different interesting data sets that provide us a unique opportunity to better understand the morphodynamics of the system. So the Rio Grande, as an international border, has been really extensively surveyed since the mid-1800s. And while in many cases its role as a border has, I think, discouraged people from going down there and trying to study it better, it also provides an opportunity because these surveys provide a wealth of information to actually extract quantitative planform information about where the river has been over the last century, but also the elevation and bathymetry of the channel and broader delta. So we're going to look at 3 historical surveys in particular, an 1897 1912 map, a 1930 map, a 1956 map, and use these together with the modern LiDAR to allow to generate an understanding of how the river has evolved over the last century. Just to zoom in on what the oldest map looks like, just because I think it's really impressive and kind of fun, you can see the wealth of information that's available to us from these old surveys. So we can see where the river was in 1912. We can see where the river was in 1897, as shown in orange here. We have dates of when cutoffs occurred. And we also have things like where floodwaters were, what high watermarks were at different flood periods within the historical record. So just an incredible wealth of information for a huge variety of studies. But for today, we're mostly going to use it for both planform location as well as information about the channel bathymetry. So we're going to use our floodplain surveys, our historical topographic surveys, and our LiDAR to characterize the Rio Grande morphodynamics through some common geomorphic characteristics, such as the channel belt widths, what the bankfold channel width is, what the levee crest elevations are, what the channel base elevations are, and then also put all those surveys together to generate a time series of how migration has occurred along this entire 300-kilometer reach. So if we look at our geomorphic data, one of the really interesting things that we observe is that the Rio Grande exhibits a remarkable linearity for the entirety of the study reach. So if we look at different geomorphic parameters, such as the levee crest elevations or the channel base elevations, both in 2011 and 1912, you can see that they maintain a constant slope across the entirety of the delta. What I've shown here in black on each of these panels is the estimated backwater length scale, or LB as I'll refer to it, which is roughly 60 to 70 kilometers in the system. And in a lot of systems, this is where you start seeing deviations in the slope, either in terms of you have increased erosion or increased deposition, depending on the flow characteristics. But within the Rio Grande, we see nothing. We don't see a change at all. It appears that the river doesn't necessarily feel that transition into the backwater transition. If we look at the bankfold channel depths and the bankfold channel widths, we see a similar story where there's just a remarkable stability of these geomorphic characteristics with no change in slope, no changes in channel geometry observed across the entirety of the study reach. So we see within our geomorphic data no evidence for enhanced deposition or erosion within the backwater transition, which is a pretty sharp difference from other more commonly studied systems. And we look at the migration rates, we can see another really interesting story. So overall, historically, the migration rates are very high and very variable, but they do not systematically decrease towards the coast. So here I have 4 panels that are showing 4 different time periods. So 1897 to 1912, 1912 to 1930, 1930 to 1956, and then 1956 to 2011. So within these 3 historical periods pre-1956, again, you can see very high migration rates. In fact, some of the highest that are reported in the literature, but no reduction in migration rates within the estimated backwater reach. So this panel with these box plots here is just showing the distribution of the migration rates above and below the backwater. And you can see that there's not a statistically significant difference between them. What there is a big change in, a big difference in, is 1956 to 2011, where you can see across the entirety of the study reach, the migration rates basically collapsed down to 0. So something really significant happened in 1956 that we'll get to later. But the important part of the story here is that we don't see in the historical river a change in migration rates or morphodynamics above or below the estimated backwater transition. This is a really sharp contrast to other more commonly studied systems. So here, I'm just plotting the standardized migration rates of the Rio Grande in black versus the Trinity and the Mississippi. And you can see in both the Trinity and the Mississippi systems, once you reach 1, which is the where it starts transitioning into the backwater, both of those systems show a really sharp decay in their migration rates, whereas the Rio Grande maintains a constant migration rate. So we seem to have no apparent backwater control on migration rates within this arid system. As a consequence of this, we have, even at the coastline, just beautiful meandering, both expansion, translation, and even loop cutoffs occurring within 5 kilometers of the coast. Loop cutoffs, like occurring this close to the coast, have not really ever been observed before, again, because most perennial systems show such an apparent stability of the river channel planform position as you approach the coastline. So what happened in 1954 that leads to such a sharp reduction in migration rates? Well, it was the emplacement of the final dam on the lower river, the Falcon Dam, in 1950, that was constructed between 1951 and 1954. So if we look at mean daily discharge going back to 1934, you can see, again, the incredibly variable flow of the river as it goes to base flow to flood. But then once the Falcon Dam was in place, we see a really sharp reduction in the flood magnitudes. If we look at the cumulative density function of those, that tells the story a little bit more clearly. So pre-dam, you can see that the median rates are still really low, only about 50 cubic meters per second versus the post-dam period of about 5 meters per second. But you still have the ability to have relatively high floods. In this case, about 1,000 cubic meters per second, but there's local evidence for even higher magnitudes. But in the post-dam, we really cut all those off. And so we see is that even though there was over a century of modification and significant withdrawals of the river prior to the Falcon Dam being in place, we still had a lot of sediment coming through the system. We still had a lot of morphodynamic activity, as shown by the migration rates in these 3 panels here. But once the Falcon Dam was put in, that's when we essentially froze or killed the river. So post Falcon Dam, the river can essentially be viewed as a static feature that's now actually actively degrading. And there's been a lot of challenges in terms of floodplain management and levee management associated with this. So there's a few really key lessons that we've learned from the Rio Grande. So one is that we don't see an adjustment across the backwater zone. So we see a really constant channel geometry. We see high migration rates all the way to the coast, at least prior to 1954. And we see a constant channel belt width. And we believe that this is linked to the high variability of discharge and sediment transport. So the channel, in essence, remains adjusted to the flood discharge and transport. And so during peak flows, that backwater transition is pushed all the way to the mouth, but base flow is not really capable of affecting significant geomorphic change or sediment transport, in contrast to systems that have a much higher base flow. And in the post-1954, the Rio Grande is essentially just static or degrading. So we almost never flood the floodplain from the river itself. We have very minimal bedload transport, essentially no bar growth, and no associated lateral migration because of those 2 factors. So a few conclusions to wrap up so we can get to some questions. What we saw from the marine realm is that the submarine slope is the main repository of this continental scaled system during the Pleistocene, and that the submarine sedimentary system appears to inherit the evulsional style of the Rio Grande Delta. So in contrast to other systems, we see no canyon incision. We see no locking in of a bypass zone at the upper slope. Instead, the upper high gradient slope is where all the action is happening in terms of actual deposition and sequestration of sediments. The Holocene Delta has at least 13 evulsions preserved on the surface, which gives us about a maximum evulsion timescale of only about 500 years, and some are likely a lot younger than that. And these abandoned channels formed by the evulsions remain conduits for fluids and sediments during those floods. So they used to help build and degrade the delta really far away from the main channel without necessarily the main channel having to come back to that portion of the delta. These intermittent distributary channels then really help to control delta hydrology and wetland habitat distribution, which again, post-1954 has been affected pretty significantly. And there's definitely a lot of ongoing work trying to understand that better and try to understand what environmental flows to those resakas looks like for management purposes. And finally, we see that the punctuated flow of the river drives really interesting morphodynamics that are different from perennial systems like the Trinity or the Mississippi. We see that this punctuated flow drives coastal meandering cutoffs. We see that the constant channel geometry of the river shows no deviation or no change in either apparent enhanced erosion or deposition once we reach the backwater transition. And so if we go back to that cross section by Marissa Rapash, we can see that we've now kind of extended out that profile all the way into the deep marine. And we've really both looked at where a lot of the sediment generated from the system has gone, but also we've generated a lot more questions about what's been going on within the system that these repositories, both within the delta as well as the deep marine, may have an opportunity to answer. So there might be some really cool opportunities for going out and back into the system and trying to answer questions about the evolution of North American tectonics, North American climate, as well as trying to better understand the dynamics of a system that appears to deviate pretty significantly from that more common canyon model. So with that, I'd like to thank everyone for joining us today, and I think both David and I would be very happy to take any questions.
Thank you very much, John and David. This is a fantastic, a beautiful case study from source to the sink, particularly in the offshore, the canyon system. In this talk series, we have a couple speakers, couples webinars, all the way from Gulf of Lyon, given by the Professor Sedibene, and also Mohrig talk about the Nile River in the western, the shelf of the Israel, and also Peter Clifton talk about Indus River. That's great. And also Peter Tolling talk about the Congo and other canyon system. Now we get better and better understanding of the canyon, how the role deliver sediment to deep sea. So I know now it's almost 10, but if you have, I know some have to leave before 10, for class. If you want to ask questions, please jump in. Don't feel shy and ask a question now. You can unmute yourself and go ahead to ask David and John. Go ahead. Just.
Can I ask one?
Sure. Go ahead.
Yeah. I was wondering, in that system, this semi-arid systems, there are a lot of, you said so, there's a lot of flooding. What's the importance of this extreme events to shaping of the river system in itself? You said that it was evolving very quickly, and also on the delivery on the margin and slope, on the partitioning between the delivery on the topset shelf and the slope. Do you have an idea of that? Well, what's the role of these extreme events?
Yeah, so in answer to your first question, I think the modern river is entirely shaped by the floods, or at least it used to be. As I mentioned, the kind of constant channel geometry appears to be a result of those floods, and it doesn't really adjust back to base flow because base flow within the lower river isn't really capable of affecting significant geomorphic change. So the floods really set the overall geometry for the entire river. For your second question about what the role of those kind of punctuated floods are for the delivery of sediment into the offshore, within the modern system, I'm not entirely sure. I think I haven't really looked in detail about what the kind of sediment delivery was out into the broader shelf. In part because that data is just a little bit hard to come by in this portion of the world, as well as the fact that post 1954, there's just not as much of delivery through the lower river out here. Like this portion, I'm looking at the mouth of the Rio Grande within this image. And this portion of the delta has been really rapidly retreating recently, simply because there's just not that much sediment load within the modern river anymore. And that was not the case prior to 1954. So maybe David has some more thoughts on that, but I haven't really looked at that in more detail for your second question.
Yeah, I think John answered the second question as well as it can be answered right now. That seems to be a little bit of a gap. And I do want to make the point again that John made that this river is different than a perennial river. The Mississippi, the Trinity, and others that have been published on showing backwater conditions, the long profile and the channel cross sections have really adjusted to handle the low flow, to get the low flow water and sediment to the coastline. Here we have a system with very little low flow water or sediment. So as a result, we have a very different long profile and cross-sectional characteristic to the channel form itself.
Okay, great. So we know Jim Best already sent me a text message. He said, thank you for giving a great talk today. And he has already left. And also here we have John Shang here, also great. Rebecca said great. And, Shang. Okay, anybody have a question want to ask Dave and John directly? Go ahead. Michael, okay.
Yeah, great talk. A lot of similarities since I work in Bangladesh, which is also a monsoon-dominated seasonal system, and it's a lot of similarities. But what I was going to ask about is, you showed sort of, up to 20 meters of sediments accumulating not at the river channel, and it looked to me like, that corresponds to sort of 2 to 4, since 7,000 years ago when sea level was basically stabilized, implies 2 to 4 millimeters of subsidence. So is that due to the growth faulting that you're seeing in the subsurface, essentially creating the space for those sediments and keeping the entire system active even when you're not in the main channel?
Yeah, that's a great question. So I think first of all, I'd like to say that our portion of the story about the Holocene delta evolution is still a work in progress. We're still trying to wrap our heads around some of the old data from the 70s that we have access to. But I think my preliminary observations and interpretations of it is exactly what you said. It seems that the old channels and the old delta surface just seem to be kind of just really keeping track with what the sea level curve was in this region, which implies, it's both keeping track of the accommodation generated by sea level rise, but it's also then has some degree of subsidence associated with it. The exact balance of that, I think we'd have to do some more work to better understand, as well as get some new dates, because the original dates were very sparse and relatively spotty. But it does seem that once the delta arrived at this kind of current position, it did just kind of keep track and just a grade in balance with subsidence and sea level rise for several thousand years.
Great. And next we have John Shang. John, go ahead.
Great talk. I'm interested in the salt tectonics. You show that the delta sedimentation overwhelmed the salt tectonics in the Rio Grande system, but it's not universally overwhelmed. So is the salt tectonics the same everywhere, or is there coupling between the massive sediment source and the deformation? That's my question.
Yeah. So thank you, John, for that question. It's a really good one, and it's actually one that we're trying to get a sense of experimentally to look at this link. There's clearly a coupling between the sedimentation and the deformation of the mobile substrate, and it is a function not only of sedimentation rate but the thickness of the deformable substrate beneath. And what we need to do to understand this system more completely is ultimately try to get a sense of what the spatial variation in thickness of the salt between the area dominated that makes up the ramp is compared to that on either side. But at first blush, it really does look more similar than different in terms of the salt thickness. So this really does seem to be a case where the rate of response of the deformation associated with the mobile substrate and the construction of topography is outright winning. So we should be using this as an example to, flip it around and say, here's a place we can actually go to understand this new kind of morphodynamic system where the substrate itself has behaviors that we don't normally don't normally put into our models.
Good, great. And here, Bob Eller, he has just left. He said, extremely interesting and very impressive. And so for those on our YouTube channel watching the live stream, if you have any question, you can type the text there. I read your question for you. But here, David and John, I have a question. You mentioned, the channel, offshore channel, mainly active until 11,000 years. That means the beginning of the Holocene. So my question is more specific. So you think about offshore channel, was it mainly formed during the sea level fall, the regression process, or the post-glacial sea level rising process, the transgressive process?
Yeah, that's a great question. So I think David probably has thoughts on it, but if I have the first crack at it, I think it probably was active throughout the kind of LGM, so like at the sea level, the sea level low stand, and then through actually the most rapid part of the transgression. So if we look at the dates of it, I don't have a sea level curve here, but if we look at what the dates of these delta systems actually were in terms of when they were still active at the shelf edge and actively transporting material and forming these submarine channel systems, they actually persisted for quite some time through the most rapid part of the early transgression post the last glacial maximum before relatively rapidly shutting off and moving back. And so I think what we are seeing there is not really necessarily like a signal of the transgression driving the behavior of this system. I think we're likely seeing some manifestation of a climate signal, like some really, sharp decrease in the basin hydrology that's leading to lower discharges and lower sediment transport that force the backstepping to our current position. Because it seems that the delta was more than happy to remain active at the shelf edge through some relatively high rates of sea level rise.
That's great. And I just want to add, do you remember in 1960 or 70, Miliani, that the paper talk about the Mississippi River, that during the post-glacial melting ice, there could be a pulse, melting water pulse shooting to the Gulf of Mexico through the Mississippi River. Did you we see any signal of that suddenly meltwater from the Colorado mountain through the Rio Grande coming down here and help facilitate the formation of those canyon or channels?
Ooh, that's a really interesting question. I mean, the patterns of glaciation within the Rio Grande Basin are interesting, but I'd say not entirely understood. Like there's some evidence for glaciation within even the Pecos Mountains in New Mexico and Texas. However, I'd say that I think the channel formations and geometries that we see, David touched a little bit about this, but they seem relatively constant in terms of what we see on the modern surface is very, very similar to what we see even 500 meters in the subsurface within the slope stratigraphy. So it doesn't seem like these channels have a morphology or are related to kind of sharp events. They just seem to be reflecting what the business as usual was of the delta system as it was active for some time.
Good.
Yeah, I would say just adding and agreeing with what John said, but adding on that, one of the things that colleagues of ours are certainly interested in is using detrital zircons, if we can get them from core to actually ask questions like that, because the detrital zircon work has been very useful in looking at those pulses down the Mississippi. It is something that we can potentially do in a system like this as well.
That's very good. So anybody else, if you have a question, please just go ahead and unmute yourself or raise a hand or whatever, just go ahead.
Right. So in terms of the system during that LGM, through the mid Holocene, are you able to break down the sediment budget at all to see whether or not the sediment supply is keeping up between the changes in the hydrology and perhaps additional sediment from a ravinement as the system backsteps, as to whether, the sediment, what the sediment supply is doing during that rise and backstepping period, because it may be decreasing or increasing, and I have no idea.
Mhm. Yeah, that's a great question. I would say I haven't really looked at that element of the detailed sediment budget in detail. I think there might be an opportunity to look at that, especially in the offshore. Because I think if I can go back to, let's see, especially at the upper shelf edge, right, we have a really interesting and impressive Holocene mud blanket that seems to be reflecting the, what sediment was coming out of the delta as it was backstepping. So I think with further work, there could be an opportunity for trying to kind of close that a little bit and really look at what that change in budget was with potential changes in climate within the basin. But I haven't looked at that in particular.
If I could just add, part of the reason why we now have a much better record than we did even when we started this work is the high resolution bathymetric data that John shared, the 2 meter isobaths. I mean, that's a very recently generated map, and now with that map we can go back into the seismic data and start to petition out these different deltas associated with a grading more or less in place, a little bit of backstepping, but a lot of a grading in place as sea level went up. But we're ultimately going to be limited when it comes to doing our mass balances by the seismic data itself. This is industry data that's shot for greater depths, and there's a water depth, certainly somewhere between 50 and 100 meters, where we just don't get recovery of enough information of the seafloor in that data. So we basically have a blanking distance without going out and collecting more data.
Great. So any more questions and comments? And I think this is, again, the very, very impressive data set. And this is fantastic all the way from source to sink. And we need this kind of study in more system like this. And so once again, this talk is archiving on our YouTube channel. It's just tiny URL/S2S talks. The edited version is over there now, and the edited version will be available online after 24 hours. And once again, so if you have some postdoc, student, or colleague, even retired colleague, and if you think they should contribute a talk, particularly our women colleague, our color people, our unrepresentative colleagues, please recommend it to me. And we will try to schedule them. And once again, this coming Friday, Christoph will talk about Congo River system. That will be very interesting. It's all linked together. So if you know any other question, I think thank you, Dave, thank you, John, thank you all the participants. That's great. And so I'll see you Friday and next week. Okay, thank you.